Well, good morning. It's good to be back here in Barcelona. It's one of my favorite places to visit. Any excuse I can, I try and come back here. So, State of the Union. So today, I think I'd start off with what is RISC-V? Some of you may not even know what it is. I'm always surprised. There's always people who show up who are just trying to learn about what is RISC-V. So the quick summary is, it's a high-quality, license-free, royalty-free ISA originally from UC Berkeley. The standard is maintained by the nonprofit RISC-V Foundation. We designed it to be suitable for all types of computing system, from microcontrollers to supercomputers. I'll talk a bit more about that. There's a lot of cores out there available, proprietary cores and open source cores. It's not only an open source core project. People often get confused about that. There are commercial companies, multiple commercial companies selling soft cores, chips, and you can also there's a large number of open source cores as well. Very rapid uptake in industry and academia. We'll give you some flavor of that from the membership, but there are many, many projects going on. It's incredible to see the momentum across the entire industry. Pretty much every company who's involved in semiconductors is looking at RISC-V very seriously. And the other amazing thing is the great support we've had from the software ecosystem. So the real jewel in the crown of RISC-V is not the ISA spec, it's the software that's being built to that spec, which everybody building hardware gets to share. The other thing is it's still a work in progress, and I'll talk more about that in this talk. So what's different about RISC-V? Well, in some ways, it's a very boring RISC, and we made that a boring RISC deliberately because RISC was a good idea. So we didn't want to mess things up too much, but things that we did was really focus on keeping it simple. So it's a lot simpler than conventional ISAs, other commercial ISAs. It's also a clean slate design. We had the advantage of sort of starting from scratch 30 years after the last batch of RISCs. It's a very modular ISA. I'm going to talk about that. And the idea is we actually designed this for extensibility and specialization. The project this came out of was looking at custom engines to do acceleration of various kinds. And we designed this to be the base ISA on which we'd add these extensions. So it's very modular. Another attribute is it's stable. So we wanted this anyway for our own purposes, but we tried to keep the base design frozen, and then the extensions, as they're developed, eventually get frozen. And then we grow the design by adding new extensions rather than by futzing with the existing ones, right? The other big difference is community design. And so, although the original design came out of Berkeley, there's been a lot of input from many people. It's been a lot of fun to work with lots of people as we plan out the new features in the ISA. Now, the timeline of RISC-V, just to give you the history, we started this project back in May of 2010 at Berkeley. That's when we sort of finally got fed up with hacking on existing ISAs for our projects and decided, let's do our own clean slate one. The first tape out of a RISC-V core was in 2011 in 28 nanometer, and this was version 1 of the ISA. The first tape out of Rocket Chip, a lot of you have been using Rocket Chip, which is the open source code base from Berkeley, chisel-based open source code base. The first tape out of that was a year later. The first Linux port was about a year later. And then in 2014 was really the year in which we launched this out into the world. We had a lot of interest. We had developed this only for ourselves, but in 2014 we decided to make a more concerted effort to tell everybody what we'd been up to. So we published the spec 2.0, and we unilaterally declared this was perfect and we're just going to freeze it. And then at Hot Chips in 2014, a bunch of us ran around trying to convince the attendees this was a good idea. And we had a very, very, very strong reception, exceeded what we expected. And so then we started holding workshops. So the first workshop was only in January 2015. So just a little over 3 years ago was the very first workshop. The foundation, we set up the foundation. The industry people told us they needed a more stable base if they were going to use this seriously. They needed something outside the university that would be a long-lived organization to help manage this standard. So we created the foundation August 2015. So some of the big highlights in sort of RISC-V uptake was at the MIT workshop in 2016, NVIDIA announced that all their future GPUs will use RISC-V as the microcontrollers on the GPUs. So NVIDIA basically declared we're going to move to RISC-V instead of using their own internal RISC core. Commercial software started appearing in 2016. The first SoC came out at the end of 2016. We published the privileged architecture 110, and this was intended to be a stable base from which time forwards we try and be backwards compatible. So at this point we had sort of the basic user ISA, the privileged architecture wired down. Then the big announcement at the last workshop was Western Digital announcing that all their future products would eventually move to RISC-V. And then we had the first commercial Unix SoC come out at the start of this year from Sci-Fi. And so there's been this transition from originally from Berkeley, now spreading out through the world. People have been using RISC-V. It's a very short time frame from when this started to the rate of adoption has just been incredible, far beyond what anybody expected. So here we are at the 8th workshop. It's already at the 8th workshop, and as you hear, we'll be moving to a different model this year. And it's great to be here in Barcelona. Great city, great place. So our modest goal, eventually, we came up with this idea that we should just be the industry standard ISA for everything. And so how's it going? Well, it's been going pretty good so far. I think my analysis is it's looking great, but there's still a lot of work to do. Okay. Now, this is a great city to come to because the residents here really appreciate wonderful architecture, even if it's not quite finished yet, right? So, hopefully we'll take a bit less than 150 years, whatever it's been, to complete this. But I hope we're still around, and I hope to be around, well, hopefully ISA is around another 150 years as well. Okay. So actually, to move to the more serious part of the talk this morning, I wanted to talk today, spend some time talking about standardization and compliance. So we're getting to this point in the ISA's development where everybody is really worried about, is this thing going to settle down? How are we going to know we have a compatible core? On the hardware side, you have companies investing a lot of money in building products. And on the software side, a lot of people, teams are investing a lot of time and effort, money, building software for this. And the real value of RISC-V, if you get to the core of what's important about this, it's a standard specification for an ISA that provides this connection between hardware and software. And making that an open standard is really the big strength of this project. So the questions you get asked are, okay, so you designed this thing for customization, but you want to make it a standard. So how are you going to prevent fragmentation? You have standards, people messing with it, adding their own stuff. And what is a RISC-V compliant processor anyway? What does that actually mean? So I think one thing that does confuse people, and we were probably confusing ourselves when we started this out, is there was a design that we did at Berkeley, which was a philosophy of how the thing should work and all the pieces fit together. And that was what we wrote about in the specifications that came out of Berkeley. And when we came out in 2014, we just decided a good thing to do with an ISA is to freeze it and not keep futzing with it. So that's what we did with the base ISA. So that's taken off. And over the last 4 years, people seem reasonably happy with the base ISA. It's not perfect, but apparently it's good enough for a lot of applications. Now, the design that came out of Berkeley, what we have to do in the foundation now is, from all the possible things the design let us do, pick some subset and things that we're going to standardize and say, this is what you need to have in RISC-V. Now, along the way, there was a bunch of problems with the Berkeley spec, and with the greater community, we worked through a bunch of holes in the design, ambiguities, things that were missing. The very big one was the memory model. I have to thank the memory model team, led by Dan Lustig from NVIDIA and Arvind from MIT. And a lot of other people helped a lot. That was a big chunk of work that's completed now. Other little things like how NANDs are handled. So at the foundation now, we have to pick out what is going to be standardized and in what units are we going to build this standard. Because it's a modular ISA, so pieces are going to be standardized chunk by chunk. So I thought it'd be good to give people some of the terminology behind RISC-V standardization and ISA. There's a lot of confusion I see on the mailing lists and in talking to people. So here's some terminology. Standard is something defined by the foundation. If something is reserved, it means the foundation has the right later to say some standard fits in this part of the encoding space, right? If it's custom, it means that this part of the encoding space, the foundation is never going to put anything in there. So if you put something in there, you can be guaranteed that all the future standard extensions can coexist with your custom stuff. Now, there's no guarantee that your custom stuff will work with somebody else's custom stuff, but that's just the price you pay for having a distributed, way of using this space. All right. So just to give you some examples here. So imagine this space is a reserved instruction space, and over here we have the custom instruction space. So somebody may come along and build a core and say, well, we'll pick from a catalog of standard extensions. Here's the base, RV32i. is M, A, F, D. These are various instruction set extensions, so I'm going to have those in my machine. I also have my secret source custom instructions I want to use in this application, so I add those over there. Now, the important thing about the design is all the standard software is going to sit and use the standard pieces of your instruction set. On the side, you're going to have your custom software libraries, but they don't really interfere with the standard code. So the model is there's a portion that's standard. The standard software just worries about that. It ignores the rest, and everything is fine. Let's take a second example. So here's the reserved space, the custom space. So this time I decide, well, I only want I, M, and A. That's all I need in this application. I have my custom stuff, but you know what? I have a really extensive set of custom things I want to do, so I'm just going to stomp on the reserved space and add in my non-conforming extensions. So what happens? Well, you can use your standard software. You just tell it, only these pieces I only have these pieces of the standard, and your custom libraries drive everything else. And this is fine. We have no problem with this. This is fine. It's your own responsibility as an implementer to realize that if some other standard part gets defined that you want to use, it might stomp on part of your non-conforming extension. But for some products, some projects, you don't care. It's just going to be something that's going to be put in some chip. Firmware is never going to be touched. The next time around, you're going to change it. It's up to you. We give you the freedom to do whatever you want there. Just don't expect us to care about what you did in that space, because we've reserved that already for ourselves. All right? So later, we may stomp on it. So I think I'd like to get across to people the big tent idea. So we want to enable as many people as possible to use RISC-V in as many ways as possible. Right? And what I've seen is a tendency to imagine your world is the entire world. There's many different parts of the processor design space. There's many different communities. There's many different needs. And so there's a tendency to say, you can't do that because it'll mess up my world. And we're trying to design it in a way that it doesn't actually mess up your world. It's OK for them to do what they do. It's not going to mess up your part of the space. Right? We want to enable all types of RISC-V implementation. So 32-bit microcontrollers with 1 kilobyte of RAM. Perfectly valid design point. There are people building this right now. 64-bit Unix servers with virtualization, perfectly valid use of RISC-V. You want to build a 128-bit address space, 100,000-core supercomputer with petabytes of DRAM, that's great. You want to support fully open platforms with fully open source software, that's great. RISC-V will enable you to do that. You want to have a fully locked down platform that's some kind of completely trusted doing DRM, that's great. You want a platform where you have to pay as you go to use the hardware, that's great. RISC-V is not taking a stance here. We're just doing a standard that could be maximally used across the whole space. You might have extensive non-conforming extensions. That's fine. You just have to be careful and realize what you're doing in terms of what will later happen in the standard, right? You may just have a software implementation. You may want to run a container in the cloud that's RISC-V compatible, running on an x86 server. That's also fine, right? So the thing to realize is you want to enable most people to get the biggest benefit about everything that we're building. Right? We're not trying to exclude uses from RISC-V. Okay, that's not the job of the foundation. We want to minimize the wasted work across humanity by maximum reuse, right? And part of doing this, and this is part of the reason we've had a bit of trouble getting through compliance, is we really have to factor out platform-level requirements from the ISA modules, right, in doing this, okay? And we want to use these standard platform profiles to reduce ecosystem effort. So I'll talk a bit more about what I mean by this. But I think the big thing about this slide is we want to enable as many people as possible to use RISC-V. We're not trying to exclude people for ideological, political, whatever reasons. It's meant to be for everybody to use as they see fit, okay? So ISA compliance, we want to separate compliance into instruction set and platform. And the reason we do this is ISA compliance is a bit easier to reason about. So a system's minimally compliant if it runs RISC-V unprivileged code correctly. So for example, that would tell you that GCC compiled code for that set of instructions would run correctly, right? And so pragmatically, what does this mean for compliance? It just means that if I give you the code, the memory image for some RISC-V user program, you should somehow in your platform be able to put that in memory, run it, return the result, so I can tell that those instructions executed correctly, were encoded correctly and executed correctly. Right? Something in the platform, from the compliance suite perspective, it's how you run that compliance suite is up to the platform. But once you run that image, you should return the results everybody expects. Right? And so really what this means is one set of unprivileged ISA compliance suite should be able to run on any platform. Now, there is challenges. Some of the things we talked about, handling a platform that only has 1 kilobyte of RAM and showing that it's compliant. That's kind of a challenge in how we structure the compliance suites. There's maybe things we can talk around how to handle that. And similarly for the privileged ISA components, they're a lot harder to test in this model, but we can do some tests that can be reused across multiple platforms to help you verify privileged ISA components. Now the platform compliance, this is something I think that we've had a lot of difficulty reasoning about. I think ultimately, my understanding comes around to a platform spec. You have a platform spec to give you tight constraints on an actual system to help with some software ecosystem. Right? There's some software ecosystem wants to know, I don't have to worry about all those variants and all those extensions. I just want to know for my world, my software world, this is what I require from a RISC-V platform. And it's really about each of those software ecosystems have their own needs in terms of what the platform should provide. So that should be really defined by each of those software ecosystems. What is a platform? So now you don't have arbitrary choice in building a platform. Like some parts of the ISA are designed to work together. You cannot leave out some instructions because the compiler won't have a clue how to compile code unless you have all of this set of instructions. That's part of the reason the extensions are bundled together the way they are. Now the privileged architecture is something that it encodes pieces of the platform, and this will vary widely from different platforms. You know, one size does not fit all in the privileged architecture space. Timers, counters, going from tiny microcontroller to 100,000 core supercomputer, you need different things, right? So we shouldn't expect this to be common across all the platforms, but where the pieces are common, we want to avoid unnecessary duplication. So when you can reuse something, you should, and you should only add something new when you cannot do it with what's already there, right? So part of our goal is to try and minimize this unnecessary duplication. So this platform compliance test is really something that the software ecosystem has to tell us what they want and what needs to be done, and they should be help authoring these tests. So, for example, one thing we need to do is build, say, a server platform specification and a compliance for that server platform, right? So something to do in collaboration with the people who are going to be building the server software. Like, what do they need to be fixed in that server platform? Or, for example, say you're doing an IoT node using Zephyr OS. What does Zephyr need to run? What does it want to have standardized in a RISC-V platform that Zephyr runs? So these are very different platforms, different needs. And this will result in different platforms that we need to standardize. So in RISC-V land, software is king. So, I see a lot of, it's great that people enjoy designing instruction set architectures. But if you build it, they might not come, right? So there's really no point adding instructions if nobody can use it. We don't repeat mistakes in proprietary ISAs where, here you go, here's a whole bunch of instructions, and then community's like, sorry, those were the wrong instructions, try again. At the minimum, the ISA extension is going to need some compiler linker or library support. These proposals, they have to be sensible to implement in a pipeline. The other thing is when you propose something, you realize you're asking all these big companies around the world to put this into their cores, right? And it has to make sense in all these different styles of implementation, or at least for the ones for which it's targeted. Similarly, the platform standards, there's no point in proposing a platform if you don't know what software ecosystem you're trying to support with that platform. So you have to figure out what am I trying to support by defining some platform, right? And standards take time. Co-develop, evaluate, and iterate. You won't get it right first time. You'll come up with a spec. You have to work with the software teams, figure out how it runs. You look at the hardware implementations. Does it actually work well in hardware? So this takes some time. And there's no point in rushing just to have a frozen bad standard, okay? But the other side of this is you do have to finish, otherwise there's no point doing anything, right? If you never finish, nobody can use it at all, right? So, finish now is better than perfect sometime, right? So there is a trade-off here we have to make. Another thing I want to talk a little about is open source hardware. So a lot of people are excited about RISC-V because it's, the most successful free and open ISA so far. It's not the first, but I think at this point we can declare it's the most successful. And it's really being seen as a key component of this nascent open source hardware community. But I think what I see is a lot of people coming from open source software community and expecting things to be the same. It's different in hardware. Some things do translate, but some things just don't work. And this is new ground. Having a common instruction set that many companies will implement, where none of them control this, right? And they have, through the foundation, they have some input, but nobody controls this. And they're making very large investments in hardware artifacts that you cannot change once you manufactured and shipped. It is different from software, right? There's also the patent lawsuit issue in hardware is very different than in software, right? Very active people are very worried about this because manufacturing things involves real money. Real money means people can point at that and say, we want a fraction of that as damages. So it's very different than the open source software. So please be aware that bringing your open source software, it's great, that ethos, but the practicalities on the ground are going to be different in this space. Right? So talk a little about where we are with RISC-V. What we said we'd do in 2017 was really the start of legacy. Besides 2017, a lot of stuff we're going to settle down and fix. And then from then on, we have to be backwards compatible with what we're doing in RISC-V. So we spend a lot of time fixing holes in the user ISA. We believe there's no implementation-defined behavior left in the user ISA, and we don't expect to change anything as we go through ratification. With 110, we said, that privilege stack, there'll be no updates except to be backwards compatible with that 110. Memory models are now completed. They're going through ratification, so please go read the specs and let us know if you have any worries about that. The Linux API was frozen in order to enable the distributions to do their work. The debug spec was completed. It's going through ratification. And so you don't get to rip up and start again with this stuff, at least not for a while, right? So, we have a lot more work to do. To revisit a lot of these decisions is not really helpful. So we'll move on and help build more of the world that we need, right? So in 2018, talking about that, we're preparing the base for ratification. That work's in progress. The formal spec is in progress. Hypervisor, we have a spec, but we're not going to freeze in spec until we have hypervisors ported and some implementations done around that. There's been some iteration. The hypervisor authors are involved in the design of this, but we need to go through and actually build this. The vector spec is getting very close. And again, though, we need some implementation compiler work before we're going to go ahead and freeze this. Crypto is in progress. We started up a group on dynamic translation, another group on packed SIMD. Security task group is in progress. So there's a lot of work going on and new pieces. Some of these are going to take a bit longer than others to go through because they're more complex chunks of ISA design to do. If you go look at how long it takes an industry to do these things, they're multiple-year projects, any of these things. And we shouldn't expect, we have a higher standard, we have more people providing input. It'll take us comparable time to finish some of these things. One thing is that the last year we spent a lot of time trying to sort out the Linux-based platform because there's a long lead time in getting everything going there. I think this year we'll spend a lot more time on embedded platforms. There's already task groups started to look at faster interrupt handling, the packed SIMD extension. Other things we've been thinking about is we probably need a different ABI for embedded than we're using in the Linux space. We want to build on RV32E. That's the kind of neglected stepchild of the ISA family right now. Compression could do some work, and I think a lot of it is we haven't spent time on the compilers or libraries, and we've seen big benefits from working in those spaces with the existing ISA. So we need to do that first before we propose any changes in compression or new things in compression. So we've been growing very fast. So Rick mentioned some of these things. So expand the foundation. There's so much stuff we need to do where the demands are outgrowing the capabilities of the organization at this point. So we're trying to radically increase the size of the foundation to support many initiatives. And Rick mentioned some of these things that we're doing. So one thing I want to highlight is RISC-V and security. The whole board figures this as a critical thing, and RISC-V has a big part to play. It's one of the biggest challenges of contemporary architecture. So what do you trust? A simple, free, open ISA with publicly scrutinized security systems, or some Baroque proprietary ISA with unauditable implementations of ND-only security, right? The answer's kind of obvious, right? And RISC-V has become the center of security research. But we want to really accelerate this and help, from the foundation side, help promote and accelerate this. This is an emphasis. And so we set up a new security standing committee. Helena from Rambus and Joe Kinnery from Galway Research are the chair and vice chair. And their goal is to really push forward RISC-V in this space and really get RISC-V central, up front and central in security. We think this is a vital thing that RISC-V can do that's good for the whole planet. Some other good news I wanted to highlight. Debian port. So the guys at Debian, thank you very much. It's been amazing to watch this happen. What this chart is showing you is the number of packages ported to RISC-V as a percentage of all the packages, and we're up to around 80%. I heard, today I think we crossed 10,000 packages available in the Debian distribution for RISC-V. That's amazing. Already talked about RISC-V in education. These books are available now. Rick already did this. He stole my slides. Okay, great. The free version in Spanish. I think we'll work on the Catalan version at some point. One other little thing that happened. So we're very fortunate to have Dave with us here. And Dave won the Turing Award this year for contributions to computer architecture. So Dave. So Dave and John Hennessy, long-time collaborator. Yeah, so we want to have Dave here. So just to wrap up, so RISC-V adoption, I think it's all changed. When I talk to people in the industry, it's not so much if, but when and where RISC-V will be adopted. And there are these markets that RISC-V probably won't have anything to do with for quite a while. Like, we're not going to take over the Z-series mainframe market anytime soon. PC, Windows stuff, no time soon. Smartphone, ARM stuff, no time soon. The incumbents are there. There's a massive amount of software. No reason for people to change. But pretty much everything else, I think, is open to RISC-V. So that's it. OK, thanks.